So let's move on to another type of deep neural network. That is a deep neural network with a pre-training. Let's recall this slide. This slide that so the idea is that we want to have good intelligence. We need to have a deep neural network, right? And if we have this naive deep neural network, we will have a lot of problems in this training. We cannot directly use the backpropagation to train that. So the CNN tries to avoid this problem by introducing the local connectivity, shared weights, and so on and so forth to reduce the number of parameters that need to be learned. And another solution is that we don't want to reduce the number of parameters, but we want to introduce other way of training that. The idea is that we can pre-train the neural network. So suppose we have a very complicated deep neural network. So it is difficult to train using from the output to the input in one round of training. However, so their idea is that we can try to train the neural network part by part, train this part, using unsupervised training. So because these are the hidden layers, we don't know what we want to get for the hidden layers, so we cannot use supervised training. If we want, supervised can only be done from the final output layer. So we introduce some unsupervised training at the middle layers. So these two curves shows their experiment about using I think this 10 million training data. So they have done two experiments. One is use all the 10 million training data with the supervised learning, not the deep neural network, only 3-layer neural network with using all supervised training. And the other experiment is that they find the first quarter of the training data ignoring their labels, using them as the unsupervised training samples, do unsupervised training using 1/4 of the data, and then using the other 3/4 as the supervised training. They can get a better result. So this shows how the unsupervised training can help. And so the idea is that we introduce unsupervised pre-training for the neural network and then followed by supervised fine-tuning at the end. A famous example of this idea is the autoencoder. It's a particular type of neural network. It's a kind of a model-free pre-training. So the idea is quite simple. It's also originated from the neural network, the multi-layer perceptron. Suppose we design this particular 3-layer multi-layer, 3-layer neural, 3-layer perceptron. One layer, this is the input, and this is the hidden layer, and this is the output. The special case of this is we design the output to be of the same dimension as the input space. This is a constant. It's a constant value. It's not one of the input. So this is the input and this is output. They are exactly the same. And for this specific training, we don't have class label. We just use the input data as the training. So that is, when we apply the one sample, we want the output to be as similar to the input as possible. So this is for unsupervised because we don't have class label. We just want the neural network to reproduce the original input. But if we can succeed do this using a smaller number of hidden nodes, then if we can use a smaller number of hidden nodes to reproduce the inputs with reasonable accuracy, we get a compressed representation of the original data, right? And this compressed representation, hopefully it captures more important message So this is the idea of autoencoder. We can say this is we encode the original input using this lower dimension, and we can decode it to reproduce the result. This is what so we encode it, we get the code, and we decode it. So the training is that we calculate the error at this output, and we use the backpropagation to train this. And after train this, we remove this decode, and we use the code as the representation of the original data. So this can be done in a multiple layer way. We can train one layer of encoder, remove this decoder, and using the output with the code we obtain as the input of another neural network, and get another layer of information compressing, and so on and so forth. So that's at this we get the encode layer, the output, the decode. We calculate the error to adjust the weights at the encode and the decode, and we remove the outcode, use the weight here. So with this, we can build a multi-layer autoencoder neural network. And at the end, we add either a neural network or supported vector machine or whatever shallow method, you can apply this on the features. So in this way, we learn the features in an unsupervised way, right? Each training step in unsupervised. At the end, we build a fully connected neural network, but we build it layer by layer and using unsupervised training. This is one particular example of the so-called deep autoencoder. So from the original image, the original image is suppose it's a 2,000 dimension. They first use 1,000 nodes to represent it, and then further compress it to 500, and then further compress it to 30 nodes. And this is slightly different from the previous version of training. They use RBM training, which I will explain later, but the basic idea is the same. After this multi-layers of information compression, they get this code of only 30 dimensions. And then they add this kind of unrolling or decoding layers, and they use the original input as the desired output to train that, to fine-tune all the parameters. This is one training using RBM training, and then they do that. And in the end, they use this 30 dimensional code to do further classification. And this way is what they got as the middle layer. So they have experimented on different images. This is a simple image of just the scratches. And this is the original image. This is the output reconstructed from only, I forgot, only 6 or something. And these are the recovered from the other kind of principal components. You can only use the first few principal components to do a similar thing, right? The data and the images. This image is the original image, and this is the image recovered by this autoencoder, and this is the image recovered by the principal component analysis. So we can say that it is better with the same dimension, with the same dimensionality. It captures better, more information from the original data. And I think this figure illustrates the advantage better. So these are got from the digit image. the 28 by 28 pixel digit image. They built an autoencoder from the original 28 by 28 input to 1000 to 500 to 250, and then to 2 coding nodes, and then they decode it in the unrolling, and they remove the decode, and they use only the 2 nodes, and these are the display of the 2 dimension of the 2 nodes. We can see that each color and symbol represents 1 digit. We can see at these 2 nodes, the 10 digits are well separated from each other, reasonably separated. Remember that all this training is unsupervised. So only let the input to, let the output to kind of reproduce the input. No class label is involved. And we can imagine that if we want to build a classifier based on these 2 inputs, it will be much easier. And the figure at the left side is the output of principal component analysis. We can extract the first 2 principal components as a representation of your data, and do the same. We can also reconstruct the image, right? And if we use the principal components, we can see the 10 digits are mixed together. It's not easy to classify them. And people have applied it on medical image data, multiple MRI images, PET image, and other images, using some pre-processing, and they use the stacked autoencoder to get the feature representation of the medical images. And use this, they use a support vector machine to do a better classification of different medical images. And these are this is the structure of their autoencoder. It's a similar thing. From original, they can get multiple layers of information representation. And at the supervised, they use the unsupervised training and use supervised fine-tuning. So this is the one way of using the model-free pre-training. And there are other methods that use probabilistic models to do the training of this. That is the so-called deep belief network. This is a family of the method. Oh, I think we are running kind of behind our schedule. So let's go very quickly. So we have a Bayesian classifier is a probabilistic model of your data. And when we have say the DNA sequence, the discrete data, we can have a Markov chain model, and we can have hidden Markov model. For example, this casino example. What we observe are the outputs of this die, and what are behind are which die you use. Suppose they have 2 die they use, and we can have this hidden Markov model of how the die, what is the probability of a die is used. And once we have a die and we have the emission probability, we get the observations. This is the generative probability model, and we want to do that from data. We want to do the inference. We want to estimate what is the die used, and we use the probability to describe this generative model. And I think we have covered this part in unsupervised. There are some terms with the same meaning, the Bayesian network or Bayes network or belief network or so on and so forth. All are a probabilistic graphic model. I will skip this. And the general case, so if we know, we have some prior knowledge about the dependence of the variables, we can have this directed graph. And if we don't know the direction, we have this undirected graph. And so with this idea, people build the directed sigmoid belief network that is like this, and we can estimate the model from the data. But this is turned out to be difficult to train this, and then people invented this deep belief network that is for some of the layers they are directed, and some of them are not directed. So they can write down this probabilistic model, and once you write down this probabilistic model, you can do parameter estimates using various type of optimization techniques like EM or MCMC. And a famous one among this family is the so-called the deep Boltzmann machine, which is a fully connected undirected graph model. So we train each sub network by using a so-called restricted Boltzmann machine. We train this unsupervised in an unsupervised manner, and then we use the output here. We train this and train this. So let's look at what is a restricted Boltzmann machine. So the name sounds fancy, but it's just you can take it as a kind of sophisticated probabilistic model. It's about the joint distribution of the nodes of two layers. Each node is a variable, right? The input nodes are the visible variables, the input variable, and we have the hidden variables. They have a joint distribution. And so the joint distribution of the visible and hidden variables is a kind of exponential distribution of this form. It's an exponential of some energy function. Energy function is defined as the weighted sum of the products of these two layers, of the nodes of these two layers, and the weighted sum of the values of each layer. So it's this is an energy function, and exponential of this we get this, right? And then we need to normalize it, of course. So this is just a very complicated probabilistic model, and no matter how complicated it is a probabilistic model with some parameters. And let's look further at what the model is like. The model is a general family of statistical of energy-based probabilistic model in statistical physics. And the Boltzmann machine is a fully connected, which means there are not only connections between different layers, there are also fully connections within the layer. So this is called the Boltzmann machine. And the restricted Boltzmann machine is that we restrict the Boltzmann machine only to those connections between layers. So in other words, in this Boltzmann machine, there's no idea of layer, just every nodes are connected, right? Now we have the layered, so we only have the node links, the edges between layers. So this family of probabilistic model is believed to, actually it's proven to be able to represent a wide variety of density functions. So it's a kind of a general form. Why people pick up this? It's kind of a general form of all the density functions you may be interested in. So we just use this form and let the data to train the parameters to decide the particular form. So the training is the idea. Although the model is complicated, the training idea is still the same. We can use the maximum likelihood estimation. That is, we find the maximum, the joint probability of of the values of the visible nodes, and and using the maximum likelihood to solve the maximum likelihood estimation, we take the derivative with regard to the parameters. Some derivation we can get. We need to estimate this probability, right? And there is a very famous algorithm that is called constructive divergence algorithm for training this. So it's very complicated, so I will skip this. But the good thing is that you can find some codes to implement that. And recently, I was just told my former student, Bai Jiang, who is now doing his PhD with Wen Wang at Stanford, they have proved that this algorithm converges. And so these are the example of using this idea to this RBM network on the digits analysis, on the digits recognition. Of course, it gets the better performance. And very recently, one of my colleagues at Tsinghua University, they applied this deep belief network on the task of protein binding, on the RNA binding protein target prediction, or the prediction of RNA motifs of protein binding targets. So they got the sequence of the RNA and the predicted 2D structure of the RNA and the predicted 3D structure of RNA, and built this network and train this network with the RBM machine, and add the label there and make the prediction. If you are interested, you can check out their paper. So so basically, I have covered the three most popular representative methods for in deep learning: the convolution neural network, the autoencoder, and this deep belief network or restricted Boltzmann machine. So actually, as we can see from the examples I have shown, in many of the examples, we actually combine the deep and shallow learning. So that is that they are not they are exclusive to each other. Actually, in this deep learning, the final step is a kind of the standard machine learning method. For example, in this one, they use the autoencoder and also use the supported vector machine. And I think this is a very impressive work, and also gives us some hints for future research tasks. This is the image of this medical image data, and what they did, what our experiment is, they built this convolutional neural network and trained this network with the ImageNet data. The ImageNet is a public database of these animals, natural pictures, objects, so non-medical images. To train this network with totally non-medical images. And then the network somehow learned, they fixed this structure, and they applied this network on these medical images, and using this network to extract the features for the medical images. And they applied supervised learning on these medical images. And then they can recognize that the network can learn to discriminate the different medical images. So I think this gives suggests that we can borrow the domain knowledge from other fields, because images are images. This is medical doctors, when they recognize, they learn how to look at the medical image. They already have all the knowledge about the natural images, right? So this is a similar thing. So I think this concludes this lecture. So any question? So because we are kind of behind our schedule, we only have 15 minutes. I will have to be hurried. But we have still. So I will go through the remaining lectures very quickly. So, so one thing I didn't mention is that all this fancy deep neural network is that behind all this, we need huge data to train them. So that's the big data issue. And the big data is really a big challenge for the for computation. And so we need solutions. It's a good thing that so we have quite a few computational solutions. One is the parallel computing, and one is the heterogeneous computing, and have distributed computing and cloud computing, and so on, so forth. The parallel computing is that we can. I think I will skip this. You can read the slides basically. So Dr. Zhang is an expert on this. So unfortunately, he cannot come. So you just read the slides. And a more popular solution is that so-called the heterogeneous computing. Heterogeneous means they use different computing structures to solve the same problem. A very representative example is that for the conventional computing, it depends on the CPU in the computer. And now the central processing unit in the computer. And now people realize that we can use the graphic processing unit to help in the computing. The graph processing unit, traditionally it used only to display things. And the other is the FPGA is a reconfigurable computing unit. So these are some. So in the graph, in the GPU, one brand of GPU is by NVIDIA. They have the CUDA solution. It's a general solution for how to use. It's a general platform for how to use the CUDA, the NVIDIA GPU for to improve your computing. And there have been a lot of successful applications on this. You can find them on this web link. This is provided by the NVIDIA company. And one particular package is that they implemented the convolution neural network on this CUDA. And we can see this is, if we work on the CPU, suppose the performance is like, the speed performance like this. Caffe is a software for CNN developed at UC Berkeley by a student who graduated from Tsinghua University and who is doing his PhD here. And with this GPU, we can say the speed is 14 times faster than this. And the CUDA is only for the NVIDIA GPU. This is only one producer of the GPU. There are other companies producing GPUs. And the OpenCL is a platform that works with all the type of GPUs. So you may want to use that. And distributed computing is just the idea of so if one machine is not enough, we want to use multi-machines. We know we can use clusters, but cluster is relatively expensive. If we want to use a cheaper solution, is that we can use distributed computing to connect multiple personal computers into a network. I will skip this. And the famous structure for this is the so-called Hadoop structure for connecting, for distributed computing. The Hadoop is the foundation of Hadoop is there is a distributed file system and distributed data processing system. And built on this, there are a lot of applications. this is the file management across the network, and the MapReduce is the structure for the parallel processing on the Hadoop structure, and there are a lot of applications, and these are some higher level platforms based on this, and you may heard of cloud computing. Basically it's some company provides the service of distributed computing. You just order the service by your demand. You don't need to build a in-house infrastructure for that. And this is a case study using the distributed computing and GPU for deep learning built by Dr. Zhang, and some performance evaluation. So I think we don't have time for questions, and even if you have, I cannot answer questions for this part. So, but the good thing is that the computer scientists have provided a lot of tools to better enable you to do this. So in end, let's go through some resources and have some discussions. So there are some books, but these books are mostly they are on traditional machine learning. The latest progress in deep learning are, I think they are not covered. You can see the books are quite old. Probably it's time to write some book on the deep learning. And there are some reasonable reviews. Actually, they are quite good. I think that the two reviews, many of my material are based on these two reviews. One is this one, and the other one. They are very heavy reviews, but they focus on more about the theoretical part, not the practical part. They especially about how to optimize the model. You may realize that I spend most of the time describe what the model is and why people want to use this model. I just leave the how to optimize the model to some existing tools. And you can find some online courses, but these online courses, I think they are not that deep. And there are web resources for the kernel machines, support vector machines. They have a website, and they contains several very good software, public software available for support vector machine and other kernel methods. And deep learning, there is a deeplearning.net network also collects a lot of resources for deep learning. And Google and Microsoft are providing, actually they are sharing their platform, and you can download the software to use. And there are packages in R, in other, you can check out this. And yeah, for deep learning, there is so at this website you can find a lot of links, and there is a Python library and a MATLAB library, and also C++. This is a cafe developed at Berkeley. This is only for C and not for other types of deep neural networks. Programming platforms. And now let's come to the end of we have discussion. So actually, I didn't talk much about the history of all these methods. Actually, it's quite interesting. Let's have a very quick review. So regression and discriminant have been studied in statistics quite long ago. And really the machine learning idea starts from the 1960s when Rosenblatt introduced the perceptron. And at that time, there was a hot, the topic became hot. at that time for a little while. And then some people realized its difficulties. And most of the artificial intelligence people turned to the so-called symbolism artificial intelligence that is built on. They try to represent all the human knowledge in symbols and use symbol logics to do machine inference for machine translation or some other tasks, the machine learning for expert system. And that survived for some 10 or 20 years. And in the mid-1980s, they introduced the sigmoid function to the perceptron and built the multiple layer perceptron, and it became hot, really hot, in the 1980s and the 90s. And soon people realized, oops, it's run out of power. So people realized the shortcoming of artificial neural network, the shallow version of the artificial neural network. And then at that time, support vector machine starts to get popular in late 1990s and early the 2000s. And somehow people paid less and less attention during that period to neural network. But it's fortunate that some scientists keep working on artificial neural network and try to make it deep and deep. And at that time, the computing power is getting increased, and also the data accumulation is getting really big. And then we get deep learning. And now I think there are different waves of this study. And there are many challenges, as you have asked. The theoretical understanding and the design principle of the deep learning, and also for other methods, are still lacking. I think this is the thing. Many of them are based on the heuristic and trial and error. And I didn't cover any of the optimization topics. And the algorithm and the theoretical properties need a lot of study. That many people are studying on that. And implementation on big data is still a big challenge. Even we have those high performance computing platforms. And the local minima and overfitting is still a big issue, even we have the big data. So there have been successful stories published, but there have been many more unsuccessful stories that cannot be published. So because my colleagues and they have some experiments, they tried to do this and do that, a lot of failure because of local minima and overfitting. So it's really challenging. And another challenge is that although it's good to have big data, but sometimes we have to make inference based on small data. And also people are good at this. For example, if you only see me for a while and then you can recognize me, you don't need to train very long to do one task. But for machine, we still need to do very long. And there's an ultimate task that all the artificial intelligence of machine learning, their ultimate goal in computer science is to reach the so-called human level intelligence. However, when we are talking about omics data, biological data, medical data, we are trying to answer questions from the data that human cannot answer directly. That is, I call it beyond human intelligence. So it's challenging how to use the models developed for human level intelligence to on those type of data and so on. There are many. So I think we are running really late. So I have some thinking about machine learning on big biological data. So really, we have really big data, right? But what is big in our data? So so let's look at the data size. It's really big, but those data size if we look at the number of samples, it's for GWAS study, we have only hundreds, thousands, or tens of thousands samples. For whole genome, and people are going toward to sequence 1 million individual, and in transcriptome, we are still talking about hundreds or thousands of samples. In metagenome, we are still talking about tens or hundreds of samples. So the number of samples is still small. So this is what we face in bioinformatics. But in the other industry, in the computer science field, when they talk about the big data, the images, they have millions of images. Simply, for example, we have the online the styling. We can have a single day, say for the Ali, they have the single day selling, they can have this 50 billion. And if we suppose each transaction is only 1,000 renminbi, then we for a single day we can get tens of millions of samples. So in that scenario, they have big number of samples, but each sample is small. So each transaction cannot be that complicated. So although the size is the same, so I coined this term that in biology, we face the small, big data, but in the other field, they are big, small data. The image it's 100 or 1,000 by 1,000 pixels. That's it, right? It's not that complicated. But for the omics data, for each single person, we have gigabytes of data for a single person. So the challenge for biological data is that we have big in size but small in the number of samples, and we have more complicated nature of the data, and so there are many challenges. So I divided the challenges as a low level and high level. The low level is how we convert from the data to information. We have the noise, and we have poor understanding of the data items. For example, when we sequence the data, we want to recognize what is the motif. So this is what I mean by from data to information. And the high level is that we want to from, say, the motif and gene expression to their association with disease. So in that part of the task, the major task is overfitting. So I think for this high-level task, we are facing the small sample size, high dimension issue is still the major issue, for which methods like support vector machine and regularizer methods that can control the generalization ability is a better choice. And for the lower level of task, for the poor understanding of the data items, I think there is a chance for applying the deep learning method, because as shown in the a few examples, the deep band or the deep sea method, so they can collect a lot of DNA sequences with single nodes in that. So in that scenario, we can have large number of samples and relatively simpler patterns. We are looking for relatively simple patterns in the original omics data. So on that aspect, we may use deep learning method. So with this, I want to, I will end the short course by saying that there is a good opportunity or the big opportunities in this field, and also we face big challenges. And so thank you for your attention, and we are still, I don't think we have time for questions. I will be at the conference all these days, so I will be glad to discuss with you. Okay, thank you.